So the crosses we've looked at before have been monohybrid crosses because they only involve one trait. We're going to look at a two-trait inherited pattern. This is due to the law of independent assortment. Each pair of factors assorts independently without regard to how the others separate, which is what that means, and all possible combinations of factors can occur in the gametes. So this cell has two pairs of homologs, and you'll notice that they are heterozygous. So this is a big S, this is a little s, this is a big W, this is a little w. Those are kind of hard to tell without the lines over them. So big W is dominant for widow's peak, little w is for a straight hairline, big S is short fingers, and little s is for long fingers. Let's come down here and change the slide. And you see them go through meiosis. So in meiosis 1, we have one of two different combination patterns that could happen. When this splits in meiosis 1, I could have the big W's together and the little w's together in this order. I could have them in this order. It doesn't matter, but you notice as they start to line up at the poles, it starts to matter as to which is with which. So big S, big W, big S, big W, little s, little w, little s, little w. In this possible combination, it's big S, little w, big S, little w, little s big, and you go ahead and go through meiosis 2, and you see the 4 possible combinations, and then you come down to the possible gametes that can be produced. So we have this possible gamete situation, which is a big S, big W, this possible that it's a little s, little w. You can have a big S, little w, or a little s, big W. So we end up with more genetic variation when we look at more than one trait at a time. There's a two-trait test cross called the dihybrid cross. So this is where you have an individual who is heterozygous for each. And if you notice, both parents are heterozygous for both traits, the widow's peak and the short fingers. So this individual has a widow's peak with short fingers. This individual has a widow's peak with short fingers. And when we come out with the dihybrid cross, which I'll show you an example of in just a minute, the phenotypic ratio is going to be 9 of the individuals could have widow's peaks and short fingers, which is the two dominant traits. 3 will have widow's peaks, which is dominant, long fingers, which is recessive. 3 that'll have a straight hairline, which is recessive, and short fingers, which is dominant, and then 1 out of the 16 will have straight hairline and long fingers. So this is called the 9-to-3 to 3-to-1 phenotypic ratio, and it's always expected when you do a heterozygous dihybrid cross or a heterozygous two-trait cross. All right, so in this case, let's say we have an individual who is dominant for both traits. So they are homozygous for widow's peak and homozygous for short fingers. So every one of their offspring have a widow's peak and short fingers that they can pass on to them. Every sperm they have is going to have those dominant traits. The female on this hand has long fingers and straight hairline, and that's the only possibility she can pass on to her offspring. So when you cross these two, the only thing that you can come up with for the offspring, all the offspring are going to be heterozygous dominant. And we saw the same pattern when we looked at Mendel's crosses with the pea plants. We ended up with started with a purebred and a purebred. Our first generation was all heterozygous, and they all showed the dominant trait, which is what we see here. All right, so the two-trait crosses and probability laws. Probability of a widow's peak is 3/4, short fingers 3/4, straight hairline 1/4, long fingers 1/4. They're taking you through the math to see where the 9-to-3 to 3-to-1 comes from. So the probability of widow's peak in short fingers, probability of a widow's peak is 3/4 times short fingers, which is 3/4. So your probability is 9 out of 16. Widow's peak and long fingers is 3/4. Up here with the widow's peak, long fingers is 1/4, so it's 3 out of 16. Straight hairline and short fingers, 1/4 times 3/4, so there's your other 3. And then the probability of getting a straight hairline, which is 1/4, and long fingers, which is 1/4, those are the two recessive qualities, is 1 out of 16. All right, it's possible to tell by inspection whether an individual expressing the dominant allele is homozygous or heterozygous. So we do a test cross to find out if they're homozygous or heterozygous. Okay, let's look at this example. It says we have attached earlobes that are recessive. So what genotype do children have if one parent is homozygous recessive for earlobes and homozygous dominant for hairline, and the other is homozygous dominant for unattached earlobes and homozygous recessive for hairline? All right, so we already know that widow's peak is dominant, so we're going to use a big W for widow's peak and little w for straight. Okay, here's the other one. Attached earlobes are recessive, so unattached earlobes are dominant. Attached earlobes are recessive. Whoops, I should say unattached. I think they're going to use E's, but we're going to use U's for this. Okay, so go ahead and pause the video and figure out if your earlobes are attached or unattached. All right, so let's go back to the question. It says, what genotype do the children have if one parent is homozygous recessive for earlobes? So here's one parent, homozygous recessive, and homozygous dominant for hairline. So big W, big W. And the other parent is homozygous dominant for unattached and is recessive for hairline. So little w, big W, that should be a U. Hold on. Okay, so it should be a big U, big U. So when we go to do the crosses, what can the parents give? Well, this parent can either put this W with this U and you have big W, big U, or little u, or this W with this U, or this one with this one, or this one with this one, just like the FOIL method. But it doesn't matter. Every combination is big W, little u. The mom on this hand can give a little W and a big U, or she can give this combination or this, but it doesn't make any difference because every combination she has is recessive and dominant. So when you cross these and the parents have children, the only possible genotype for the offspring is going to be big W, big U, little u, which makes them heterozygous. All right, so let's look at a Punnett square that's going to show us this information. Again, I always make sure that the first one is written on the left-hand side, and we're going to put the combinations together. And I realize that we only have one type of combination possible, but I just wanted you to get into the practice of it. So a big W can go with this little u, or it could end up with this one. And you can't tell the difference between them, but it's about the pattern. Big W, little u, big W, little u. The mom, on the other hand, little w, big U, or this one can go with the second. So every box on this Punnett square is going to have, we're going to put them in size order. So big W, big U, little u. Every single box has the same thing. Big W, big U, little u. So the only possibility for the offspring are going to have widow's peak. So they're going to show the dominant trait there. And they're going to have unattached earlobes. Because that's the only possibility there. So if I were going to do this dihybrid cross, and I would fill this out, and then I would say the genotype is big W, big U, little u, 100%. And I would say the phenotype is widow's peak, unattached earlobes, 100%. So the practice problem says, if an individual from this cross reproduces with another of the same type, what are the chances they will have a child with straight hairline and attached earlobes? And the answer is 1 out of 16. So let's go ahead and set up this Punnett square. So what they're asking is, if I have an individual from the one before, which was heterozygous for both traits, and of course this isn't going to be in the same family because you wouldn't want to inbreed. We're going to do the same thing with putting the parents' information on the left side for the first one, the second one on the top. So the way that we look at this is the total possible combination. So when this goes through segregation in meiosis II, the big W and the big U could end up together. Or the big W and the little u could end up together. Same process we just used on the Punnett square before this. The little w and the big U could end up together. Or the little w and the little u could end up together. Because the mom and the dad have the same genotype, we're going to have the exact same possibilities in the eggs as well as the sperm. So we can go ahead and write those across here. And this is a classic heterozygous dihybrid cross. So we should end up with the phenotype ratio of 9:3 to 3:1. So you go ahead and take time and fill out these boxes. Now, through the amazement of modern technology, it's completely filled in. And we're going to look at the genotype and the phenotype ratio. And the genotype ratio, I'm not too concerned about. But let's look at the phenotype ratio. So physically, what do they look like? So remember, it takes only one copy of a dominant gene to appear dominant. So our two dominant traits are going to be widow's peak and unattached. So we have, if you watch the pattern, there's one here, 2, 3, 4, 5, 6, 7, 8, 9. 9 that have at least one W and one capital U. Another possibility is going to be a widow's peak and attached. So we're going to be looking for one W and two little U's. So we have 1, 2, 3. The next one's going to be the recessive, which is straight. So we're looking for two little W's and dominant, which is unattached. So at least one copy of the dominant gene. So we have 1, 2, 3. And the last one is will be the two recessive traits. So this one should be straight hairline and attached earlobes, which would be little W's and little U's, and we only have one of those left. So that helps you with your bookkeeping. And there's our classic 9:3 to 3:1 ratio for a heterozygous dihybrid cross. Look at our last practice problem. So a child who does not have dimples or freckles is born to a man who has dimples and freckles. Both dimples and freckles are dominant. And a woman who does not. What are the genotypes of all the persons concerned? Okay, so the man has dimples and freckles, and both of those are dominant. And the woman does not have either. So we know that she must be, see, little d, little d, little f, little f. And we know that the dad has to be at least have one big D because he exhibits the trait, and one big F because he exhibits the trait. So the thing they're wanting us to be able to tell from this information is this child doesn't have dimples or freckles. What are the genotypes in this for this possibility? All right, so if the dad were homozygous dominant, so big D, big F, little f, or big F, all of his offspring would have dimples and freckles because he can only give a big D and a big F. Mom can only give a little d and a little f, so her traits are going to be masked. So every offspring is going to have dimples and freckles. This child, however, does not have dimples or freckles, which means that its genotype, so the child's genotype, has to be little d, little d, little f, little f. We know that the mom's has to be little d, little d, little f, little f. That means that the dad's, in order for this to happen, he's got to be heterozygous for the trait. So he has to be big D, little d, big F, little f in order to show that trait.